overall mission to push human presence further into space. I know that you're all in favor of that. So we have here on the slide the logos for the 5 sponsoring agencies of the International Space Station. NASA, Roscosmos, the Russian agency, the Japanese Space Agency, JAXA, the European Space Agency, and the Canadian Space Agency. And then you see there the 15 countries that are involved or have supported the space station since its beginning. Did you know that it took 42 space flights to assemble the main components, the main pieces of the space station? That was done by the space shuttle, which we'll talk about in a moment, and also the Soyuz rockets that were from the Russian Space Agency. On the outside of the ISS, there are 8 solar panel arrays that power the space station. And together they create up to 90 kilowatts of electricity, which is enough to power an average of 13 homes. The space station allows 6 spaceships to be connected to it at once, and these spaceships can bring people and supplies from either Russia, Japan, or the US. And as of April of this year, 240 people from 19 countries had visited the space station, many of them multiple times. The US sent 151 people, Russia sent 48, 9 were Japanese, 8 were Canadians, 5 were Italians, 4 were French, 3 were German, and there were 1 each from Belgium, Brazil, Denmark, Great Britain, Kazakhstan, Malaysia, the Netherlands, South Africa, South Korea, Spain, Sweden, and the United Arab Emirates. So good representation of our global space faring countries there at the International Space Station. Okay, this next slide does a little comparison for you that give you some scale, the size of the International Space Station. It's 356 feet wide, about the same length as a football field, and just about the same width. Boeing 747 by comparison is 232 feet long, and the Statue of Liberty, if you laid it down on its side and compared its length, was 305 feet. So the space station is quite a large object there floating above our heads, about 230, 250 miles up in the above the Earth. The ISS has been called the biggest human-made thing in space, and it's the 3rd brightest object in the sky. It's so big you can see it at the in the night sky without a telescope or binoculars. As I mentioned, it's 356 feet long, 246 feet wide, and about the same size as a soccer field. It weighs 462 tons, about the same as 280 cars. Space station has 33,000 cubic feet of total space, with about 2/3 of that used for equipment and storage, and only about 1/3 of it's the habitable portion. And all that may sound big, but for 6 astronauts, it's a little cramped. It's approximately equal to about a 1,400 square foot home. So 6 astronauts in all their gear and floating around weightlessness would be kind of cramped. So, there are also science labs where the crew can do research. There are up to 2,400 research investigations going on at any time on expeditions, so the labs can get very crowded. The solar panels that you see there, the solar arrays, provide the electrical power, as I mentioned, and these solar panels are bifacial cells, meaning that they collect direct sunlight on one side of the cell and then light that's reflected off from the Earth on the other side, and making them much more efficient than the type of panels that we use here on the Earth. And then the fact that they operate more efficiently in the lower temperature also adds to their efficiency. Okay, I have a little data on the cost of the International Space Station, which I thought would be interesting to y'all, but my data is a little bit old. It's from 2015. The ISS has been described as the most expensive single item ever constructed. As of 2010, the total cost was 150 billion US dollars. That includes NASA's budget of $59 billion for the station from 1985 to 2015. Russia's $12 billion, Europe's $5 billion, Japan's $5 billion, Canada's $2 billion, and the cost of 36 shuttle flights to build the station estimated at $1.4 billion each, or $50 billion in total. Assuming, do the math here with me, assuming 20,000 person days of use from 2000 to 2015, for the 6-person cruise, each person day, so the cost to have one astronaut there a day, it equals out to $7.5 million. So quite an expensive hotel stay, wouldn't you say? Okay, the space station orbits, takes it all around the globe so that it may pass right over your head at times but it may be less visible, such as either in the middle of the day when it's too bright, or in the middle of the night when the sun is on the other side of the Earth and we don't get the reflection to be able to see the space station. The best sightings occur early in the morning before sunrise, or in the evening shortly after sunset, when the sky is dark but the sun can still reflect light off the metal structures of the space station. The ISS revolves around the Earth once about every 90 minutes. Because the Earth is rotating below it, that means the ISS doesn't actually pass over the same spot every 90 minutes. And the ISS orbits at an inclination of 52 degrees from the equator. So if we were to plot those orbits, we'd see something like what you see here in the picture with these lines of travel, the path of the ISS over the planet. Every 90 minutes, the ISS orbits at that inclination of 52 degrees. And so each orbit is offset by about 22.5 degrees west of the previous orbit. And so we can see that it pretty much covers all the habitable land masses in the world. So that's really favorable to a shallower inclination around the equator, so that unfortunately now more of us can see it. And I know that many of you have probably seen the space station. It's a regular event when it comes out. We always try to announce it, and but I gave you there a couple of websites: Spot the Station at nasa.gov and heavensabove.com. So always a special event to see the space station, watch it, maybe even try to get it in your telescope or binoculars and make out some definition or the general shape of the space station. It's quite a treat. Okay, so how would you get to the space station? Well, there's a few different ways. There's the space shuttle that was retired in 2011, so that's not an option for you anymore, but it flew to the space station 37 times out of its 135 different missions. It carried a maximum crew of 8 persons, and that was the real workhorse for building the space station and transporting astronauts and experiments and cargo to it. Once it was retired in 2011, as most of you also know, we reverted to depending on the Russian Soyuz capsules and rockets. The most reliable rocket and capsule that we've had, because it has racked up 1,700 total flights since its first inception and development in 1966. Unfortunately, it only carries a crew of 3 persons. So nowadays, we've got new methods to get to the space station, in addition to the Soyuz, which is the Russians are gonna continue to operate. But NASA has developed the Commercial Crew Program. And in that Commercial Crew Program, they're looking to private industry to create and develop the vehicles to get to the space station and then beyond. So the first one was the SpaceX Crew Dragon, which the first test flight went up on just a week or so ago on May 30th. There were 2 NASA astronauts aboard, and they're now at the space station. And then coming up, the Boeing Starliner, while it's been behind schedule and has been plagued with some problems and delays, it's still expected to launch before the end of this year on its first test launch. And so between the two, SpaceX and Boeing's Starliner, NASA is depending on those vehicles to take our crews back and forth to the space station in the future. I captured this picture off the internet. I thought it was especially picturesque of the launch of the Crew Dragon demo from the Kennedy Space Center there. And as most of you have probably either watched it or have watched the replays of it, perfect launch there on Saturday, but it was actually delayed for a few days, and you can see the sky behind the rocket there was overcast, and they were really down to the wire there on the weather conditions, because it's not just the weather conditions obviously there at the Cape, but also downrange in case they had to do any rescue or aborts. They need to have clear weather, and there at the time there was a hurricane brewing off in the Atlantic. So a little touch and go there, but NASA and SpaceX pulled it off. Okay, here's a couple of photos of the Dragon approaching and docking at the space station, and then the two astronauts, Doug Hurley and Bob Behnken from NASA, they're aboard the Crew Dragon. A little bit about the spacecraft itself. The Crew Dragon is the human transport version of the Crew Dragon capsule, the cargo version, and it's been designed to carry cargo, and it's done that reliably over the last several years. But now only 2 astronauts are on the demo at this time, but it can be configured to carry up to 7 passengers. On a NASA mission, they're saying that would be a maximum of 4 passengers plus the cargo and the spacesuits. The rocket is SpaceX's proven Falcon 9 rocket that escorted the Crew Dragon through the launch, and the Falcon 9s have successfully launched dozens of SpaceX missions, so that's going to be the workhorse going forward for SpaceX. The big advantage to the Falcon 9 is its reusable boosters that can successfully be reused because they land on a drone ship or even on land, and can be reused. So that's the whole key to the future of our commercial space, is the reusability, the sustainability of the equipment. The crew, as I mentioned, are NASA astronauts. They both flew on the space shuttle previously, and Bob Hurley was, Doug Hurley was one of the last astronauts to fly on a shuttle Atlantis in 2011. And so the goal is if SpaceX passes the muster on this demo, then NASA will certify the Crew Dragon for regular flights back and forth to the ISS. And then the space station, the space agency, NASA, is already looking ahead to the outcome and has assigned astronauts for the first Crew Dragon, the operational mission 1, which could launch before the end of the year, or as they're saying, later this fall. So we're looking forward to that. Okay. The ISS was originally intended to be a laboratory, observatory, and factory, while providing transportation, maintenance, and a low Earth orbit staging base for possible future missions to the Moon, Mars, and asteroids. However, not all the uses envisioned in the initial memorandum of understanding between NASA and Roscosmos has come to full fruition. In 2010, the United States policy, the ISS was given additional roles of serving commercial, diplomatic, and educational purposes. And so I did pick out 3 experiments that have recently been carried out on the ISS, and I wanted to share those with you. So the first one is the study of neutron stars. And so earlier this year, an experiment on the space station called Neutron Star Interior Composite Explorer, NICER for short, found two stars that revolve around each other every 38 minutes. One is a super dense spinning pulsar, and the other is a lighter white dwarf that spins around it as the larger star slowly hoovers and eats it up. The pulsars, as you probably know, are incredibly dense and fast-moving stars, usually neutron stars, that emit beams of X-rays as they rotate. And both neutron stars and white dwarfs are the endpoints of a star's life, formed when a star explodes in a supernova after burning up its fuel. We can detect a pulsar's beam from Earth, or in this case, low Earth orbit from the ISS, if it points directly towards us. Think about the light of the beam from a lighthouse as its lamp spins. And so we're lucky to have spotted this super speedy pair of stars, but the stars are closer to each other than the moon is to the Earth, and their 38-minute orbit makes them the fastest pulsar binary around. So NICER arrived at the ISS last year and is tasked with making lots of detailed measurements of neutron stars so that these two record-breaking stars might not hang on to their title for too long. Okay, the next one, number 2, that is growing plants on the International Space Station. So a single red romaine leaf lettuce might not be your idea of a really tasty snack, but for someone on the ISS who's gone months without any fresh food at all, it's probably pretty appealing. This particular red romaine lettuce shown there in the photograph was grown in a veggie growth chamber designed especially for the ISS and suited for the needs of growing food in weightlessness. The veggie experiments are all about figuring out how to grow food without gravity. And in 2016, the astronauts ate their first space-grown salad aboard the ISS. And so, because there's no real up or down in space, the roots of a seed, the roots of a plant grow all over the place. Normal water and soil would float away. So instead, plants are grown in bags of substrate that NASA calls plant pillows, which deliver fertilizer and water to the plants as they need it. The seeds would float away too, so instead of being embedded in soil, they're glued in place with their shoot side facing up and the root side facing down. And there's no natural day or night cycle of light in the space station, so LED lights are used instead and encourage the shoots to grow in the right direction towards the light. And as well as providing some much needed dietary variety for those aboard the ISS, growing food will be vital for any long duration space missions. It has the added benefit of providing a bit of gardening therapy for any green-fingered astronauts as well. Okay, the third experiment I want to highlight here is the development of cancer drugs. Scientists have used the unique environment on the space station to figure out better ways to create cancer drugs on Earth. This process of microencapsulation is a technique that involves putting drugs or other agents inside a tiny biodegradable balloon-like capsule, which is then delivered directly to a tumor or a site of infection in the human body using a specialized needle. These microcapsules can also contain contrast agents to help doctors see inside a patient's body to better track a disease and help treat it more effectively, or even genetically engineered DNA can be delivered for gene therapy. So in this experiment on the ISS called MEPS, MEPS2, the scientists took advantage of microgravity to find better ways to make these microcapsules using altered fluid dynamics and surface interactions between the liquids. They made capsules containing different anti-cancer drugs, magnetic particles designed to be released on demand inside the body, and genetically engineered DNA. Scientists on Earth have been able to recreate these methods first used in space and then resulting in better ways to make microcapsules here on Earth to treat tumors and resistant infections. Maybe this will be the cure to our COVID coming from space. NASA holds several patents for the techniques that should speed the development of cancer treatments, so more patients can avoid the side effects of chemotherapy and be treated with a targeted drug. Also, in one of my last slides, a little spoiler alert, but my last slide, I'm going to talk about one of the other benefits of the space station, and that's disaster response, or the viewing of natural disasters here on Earth. More on that in a minute. Okay, I just wanted to share a few pictures of the ISS that I found interesting. Here you see the cupola in the Tranquility module that provides an observation deck, a 360-degree window observation deck for the ISS crew, giving them visibility to support the control of the space station remote manipulator arm, and also general viewing of Earth or celestial objects, and while also any vehicles that are docking can be observed as they arrive through the cupola in these windows. And as you can see, the hatches there on the right picture are open because naturally they need to be closed to prevent the windows from being marked up by micro debris, micrometeorites, other than when they're being used. Okay, the next slide here, photograph of, you ever seen pictures of the International Space Station from the inside? You probably have been surprised by the amount of clutter and things floating around, displayed on the walls, all over the floors and the ceilings of the modules. It gives you the impression that the astronauts live like college students in their dorm rooms. But really, it's because of the lack of gravity. And so it's common to see things everywhere. They're attached to the walls with Velcro or embedded to the floor and the ceiling. And it has to be taken into account that because there's no gravity, everything's floating around, so it needs to be secured. And on the ISS, though, it's very highly organized, and it's kind of like when you were a teenager and your parents come in and tell you to clean up your room, but you say no because you know precisely where everything is. So very organized chaos there, as you can see the inside of the space station. And there have been people that go to the space station that say that there's a lot of fan noise in some places, but you get used to it. And well, I can imagine, you can see all the computers and laptops and servers, I'm sure they're on board, that each have fans. And doctors have actually identified that time on the space station can result in some hearing loss after long periods of time. Okay, so I was interested in how people sleep on the space station. The International Space Station, maintaining their circadian rhythm of their body is especially important because disruptions to their sleep patterns, as you all probably know, can lead to fatigue, mood changes, metabolic disorders, heart disease, gastrointestinal problems, not to mention accidents because of fatigue on the job. And astronauts have developed several tactics or techniques for mastering the art of sleeping in space that's also proven to be useful for sleeping here on Earth. And so the bedroom that each astronaut has is a small cabin with a sleeping bag clipped into the cabin wall that they zip themselves up in to prevent them from floating around. And then that cabin also holds their computer and has room for a small, some number of personal devices. So naturally, keeping your sleep schedule in sync with your body's circadian rhythm is the best way to prevent insomnia and fatigue. And it's easier to do that on Earth, where our bodies are naturally acclimated to the 24-hour day cycle than it is in space, where the sun rises and sets 15 to 16 times a day for these astronauts. And so maintaining that 24-hour sleep schedule may not come as naturally. Astronauts have to train their minds and bodies to maintain a 24-hour circadian rhythm to ensure optimal mental functioning and sleep quality. And they have a schedule that includes sleep and wake times, lighting, strict lighting instructions, diet, exercise, and sometimes natural sleep aids like melatonin or even prescription sleep aids. So I thought that was interesting to share with you. I wanted to also touch on what is going on currently at the ISS. So the information I found on Expedition 63, which is currently the expedition that's going on, that has a crew that consists of 2 Russian cosmonauts, 1 American astronaut, and then most recently, the 2 American astronauts that arrived on the Crew Dragon demo are there. And so the picture there on the left shows the NASA astronaut Chris Cassidy conducting an experiment, and then a photograph there in the upper right of the ISS, the current crew, and then the picture in the lower right is of the Gulf of Mexico that the tropical storm Cristobal was identified and tracked by NASA cameras there on the space station. So they're keeping an eye on the weather for us and conducting experiments, and also perfecting their spacecraft and testing it out currently. So next slide here is a picture of from the ISS of this gibbous moon pictured on June 7th. And I want to talk to you about the future of the ISS, but I didn't have any pictures that I could find that really illustrated it well. So I want you to gaze upon this kind of unique picture of the moon while I share with you a little bit about what I know of the future of the ISS. As we know, the Crew Dragon demo crew is there now. Later this year, SpaceX is going to send up Crew 1, which will be the first actual operational crew of SpaceX other than the current demo. And that mission is expected to launch in August of this year, with the exact date still being determined by the success of this demo that they're running currently. And there's expected to be 4 members of Expedition Crew 64 on that vehicle. The Russian agency Roscosmos has endorsed the continued operation of the ISS through 2024, but as previously proposed, using portions or modules of the Russian segment to construct a new Russian space station. So more to that to come, as they may cannibalize the space station to build another one. So the future of the space station is really kind of, no pun intended, up in the air. NASA has also considered using modules of the ISS for the new Gateway space station that's going to be parked at the Earth-Moon Lagrange point to serve as a base for lunar missions and deep space expeditions. And so more on that in the future also. NASA had originally planned to end public support and public funding for the space station beginning in 2025. However, it has pulled back from that position somewhat as support has grown in Congress recently for extending ISS operations into 2028 or even 2030. Naturally, cost is a big portion of the concern. The cost of operating the ISS and transporting astronauts to and from the space station consumes about half of NASA's budget, which is $3 to $4 billion annually for just the transporting to the ISS. And NASA's plan for the ISS in the future is detailed somewhat in the president's fiscal year 20 budget that requests and envisions new commercial capabilities on the space station by 2025. And we're already starting to see that as commercial crafts or vehicles are arriving, as well as platforms for commercial activities and low Earth orbits. And in addition, NASA's announced plans to host private astronauts on the ISS and provide a range of capabilities for private researchers beginning as soon as later this year. So save up your spare change, and maybe we can all chip in and get our President Mike a trip to the space station. Mike, we'll see if we can't afford a two-way trip for you.
It's okay.
Okay, this last view I wanted to share with you. As I mentioned, the ISS does work to view Earth continuously in its paths over. This is a picture that it took of California in 2018. You can make out the general shape of the San Francisco Bay and Monterey Bay. And then you also see the wildfires that were burning during 2018, that summer of 2018. And this was a picture that the astronaut from the European Space took in August of 2018. So there you can see a great view of California, probably even make out a lot of the geographical features. If you look closely, you can probably even see Doug Christensen down there at Oak Grove Park waving at the space station as it flew by. So hope you all enjoyed that update on the International Space Station. That concludes my talk. I will answer a few questions and we can move on to the next presentation, Jerry. Jerry, you with us?
Oh, I'm with us.
Okay.
Do you see any questions, Mike?
I don't see any. Does anyone? There's one from Lonnie.
Lonnie's just giving us a thumbs up.
Thank you, Lonnie. Hope you enjoyed that.
Okay, well, that was excellent. Thank you so much, Tim. Very informative, and you did a beautiful job. Really appreciate it.
Very good.
Okay. Anyway, next we have Jeff. Those of you that know Jeff know that he is a master mirror maker. I can't begin to tell you all the things he can do, but one of the things he does superbly is make telescope mirrors. I can vouch for that. He made a 32-inch for me, and the optics are superb so far. We haven't tested it thoroughly, but it's a pretty awesome mirror. So tonight, Jeff is going to speak on the Hartman test, and it's a modification of it, right, Jeff, where it's a two-dimensional rather than a one-dimensional one.
Yeah.
Why don't you go ahead and
okay.
I'm done talking. So go ahead.
So hi everybody, and by the way, it's so good to see everybody. Seems like it's been forever since we've seen everybody. So hi, and I've been missing you all. So I'm going to click the screen share, and I'm going to see if I can do it right this time. Oh baby, I think I did it. Did I do it?
We got it, loud and clear.
All righty. So this shouldn't be more than about 3.5 hours long. So, you know, sit back.
Keep it quick, Jeff.
So this is not a real Hartman test. This is my version of a Hartman test, and I'm writing a spreadsheet to do it. And the idea of this, one of the ideas is that it's a 2D test instead of a 1D test. And I can't get the screen to change. What's going on here? There we go. By the way, can you guys see my mouse arrow as it's moving?
Yes.
Okay, good. Good enough. Okay, so I currently use Bill Thomas's slit image test, and it is the bomb. It is the most accurate, repeatable, single-axis test I've ever done. I mean, Lonnie and I tested a mirror. He tested it up in Citrus Heights. I tested it down here, and we're off from each other by about 1/80th of a wave. And the repeatability is remarkable, but it only takes it across, you know, the single axis of the mirror. And so that technically is an issue. We have things like a back interferometer that gets a whole mirror, but I have found that with large, fast, thin mirrors, it's probably me, but it's a stinker. It's not working out for me very well. So I needed something that does the entire mirror, that is as fast and accurate and as repeatable as the sit test. And finding that can be difficult. So if you have a single axis, I guess you can see my face in the corner. Am I correct?
They're all asleep, Jeff.
Jerry, can people also see me in my hands and stuff?
It depends on what view people are using.
Okay, well, I'm going to wave my hands anyway, just pretending that people can see me. So if you look at a telescope mirror on the test stand, the sit test has 15 holes across it like this. And when we get our evaluation, it's on that line across the mirror. But the top of the mirror and the bottom of the mirror are not in it. And so then we also do a star test for astigmatism. And if we don't see astigmatism, then we make an untrue generalization that it is a surface of revolution and all's happy crappy. But when you do it path interferometer, you can see that there's actually, lumpiness is a high spot here, a thing there. And so there really is no guarantee, even though it visually looks like there's no astigmatism, that doesn't mean there isn't some lumpiness going on the way. So when we come up with a Struhl number, it's total crap. So I wanted something that was not a single axis test. The other thing is, and if you can see my hands while I'm doing this, the primary mirror in the shop on a sit test or on an interferometer test or in a focal test or on a Ronchi test or all these guys, the mirror is sitting with its optical axis horizontal, so the mirror is on its side. Well, for a 12-inch f5, that is no big deal. Who cares? But when you do a 32-inch f2.8, that's only that thick. That mirror sags down on the top and spreads out on the sides like a potato chip. And so when you do a single axis test, it may or may not be really the deal. So be nice if you can tilt the mirror so that it's at an angle very similar to how it will be used in a telescope. And so I do it on Polaris, which for our latitude is 37.5 degrees. If you're in Stockton, 38. Down here in Lathrop, it's 37.5. So now the mirror is at an angle that's more natural to how it's going to be used. It's now in the telescope that it's going to be used in. So if you figure the mirror to fit that, then there's no reason to think it's going to change when you use it as a telescope mirror. The other thing I like about this is I put the mask in the front of the telescope, but it's now using the primary mirror, itself, the secondary mirror, and your collimation. It's using everything in the telescope to evaluate a system rather than testing the mirror all by itself and then shipping it out to putting it in a telescope. So you can make a really good mirror and then you put it in a telescope, it's like, what's wrong? So, but if you test the entire system, then you already know what to expect. So I wanted to do this Baldwin at the focus Hartman test because when it's at the focus, then a paraboloid is null, where when it's in the shop and you have the radius of curvature, it's not. It's at the angle it will be used at. It's now using the other components in the system, and it's at the natural angle. And so a whole lot of reasons I wanted to do this test. It's taken me a long time to get around to writing a spreadsheet for it. So I'm going to go ahead and go to the next slide here. So this is Lonnie and Bill and I use this sit test. It was invented by Bill Thomas up in Grass Valley. And I'm going to put my mouse on the screen again. You have a slit right here and it shines out, hits the mirror, but there is a mask. A mask looks like that, by the way, 15 holes. And those holes reflect the light and cross. So the radius of curvature is between here and here. So if this is in front of the radius of curvature, then this is behind it. Then they diverge out. Then we photograph with a CCD camera those slit images. And so the idea is we mathematically compare where the slits images are to where they are supposed to be. And the arithmetic tells you the error of the mirrors. And so this is a slit image. This is what it looks like when you use a slit. I quit using a slit a few years ago and I use a pinhole, very round pinhole. And so instead of getting slits, I get 15 circles that are more densely saturated centers than on the edge. So what you do at this point is you take the image, which you shoot in RAW, and you convert it to a TIFF, which can have metrology performed on it. We then put it on an ImageJ software, which Jim Sieferling might have used in the day when he was using an electron microscope. And we measured the center of gravity of these slit images to an extremely tiny fraction of a pixel. And my pixels are 5,000th of an inch, and we're looking at like 1,000th of a pixel. It displays it to 1,000th of a pixel. And you'd think that's crap, but if I did it a second time, it would give me the exact same numbers. I mean, it's the repeatability is uncanny. So then once we have those pixel positions, we put those pixel positions into my Lonnie's and Bill's spreadsheet, and then it computes the slope of the mirror based on where the slits are, and then we compare where they're supposed to be. And so we not only get a Miller chord graph out of it like we did with a Foucault test, but we also get a profile graph. Only unlike, you know, if you do a Foucault test of a 32-inch f2.8, what you get is pretty much garbage. When you do it with the slit image test, it is unbelievably repeatable and unbelievably accurate. And the testament to it is when we finish a mirror and we star test it, the star test it's perfect. I mean, it's the best test I've ever used, and the only one I will use unless I can get this Hartman test up and running. So here we go. I hope that it will be similarly accurate, similarly fast, and similarly repeatable. That will not be the case, but a guy can hope, right? So as far as accuracy goes, it depends on my mask management and camera registration management. As far as how fast it is, it will not be as fast because I can cycle through a sit test in a matter of minutes and be back working on the mirror. Where if I do a Hartman test, I have to wait till it's nighttime. I have to set up the mask, set up the telescope, get it all registered. And so it's not even close to being fast. That's not its feature. And I hope it will be repeatable. That is something to be seen. It is a two-dimensional test that covers the surface of the mirror rather than just a line across the center of the mirror. Not only will it show the spherical aberrations, which is one of the primary things that you're looking for on an optical test, but it will show astigmatism. I've got a little PowerPoint movie I'll show you where you can actually see the astigmatism as it passes through focus. The mirror will be sitting in the telescope at a more natural angle. And so there's not going to be a big difference between how gravity is affecting it in the shot compared to how it's affecting it in the telescope. It's going to be at the focus, therefore a null test. And I'm going to use all the optical components. So it's got the secondary mirror, the primary mirror, the secondary mirror holder and spider, the cell, all the structures. And if something's wrong, it's going to show on the test. And so it's not just a mirror test, it's a system test. All right, so the first time I did it, I got this image. And so the mask has 8 radii, each with 5 holes. And it has a center hole because Lonnie, when he makes my mask, he machines my mask because I really stink at that stuff. So there are 41 holes. The center holes behind the secondary mirror is not used. Then, if you look in here, you can see that that one is not completely exposed where that one is. So you can see how I can adjust the mask. I can expose it and then adjust it, expose it and adjust it. But this one here, I shot on a mirror that has a turn down edge. And since this mirror has a turn down edge, I took black paint and painted the outside 8th inch of this mirror. It's an Orion XT. It's a Chinese mirror. Pretty good except for that turn down edge. And so the problem is that my holes are being partially interrupted by that black paint. And so if you look at this hole, it doesn't cut. The other thing I noticed was, well, what's all these? They all look like little itty bitty solar eclipses with a black disc and a corona around it. Oh, wow, that's not weird. Well, that is weird. So I finally figured out through some guys on our ATM group that Francis is a member of, that there's a diffraction So I started experimenting with the position of the camera, and I moved it in, and I was able to get one that looks exactly like the SIP test images. So the difference here is I just moved the camera in closer. So if you look at each dot, they are very well saturated in the center rather than being black in the center. And for using image J for measuring their positions, it's a lot better. So this is my first successful Hartman image as far as getting the spots to work out. But you can see that the night I did this, I was not interested in mask positioning. I was interested in dot images. So you can see that this guy is over the edge of the mirror and this guy's not. So I needed to shift the mask over. But even with this image, I still had that black paint on the edge. So since this image was taken, I've removed that black paint, and I'm waiting for a clear night to go out and shoot another image, at which time I should get the entire mirror without any edge blackening and with it perfectly positioned. And there was one other error that happens, and I'll show you with these upcoming files. All right, so here is kind of a picture of what's going on. My mask is actually way over here in front of the telescope with 40 holes, which means that I just put it in my screen thinking that you can see what I'm doing. So I'll use my mouse here. Like here's a hole, and so there's this little itty bitty half-inch telescope that goes right there and comes to focus down here. You can imagine there's 40 of them. I didn't draw all 40 because I was kind of in a hurry when I do this. But they all come to focus here, and then they diverge. And then my CCD images those 40 dots, at which time I could then do metrology with the image J in my spreadsheet. So that first image I did with the little, they look like total solar eclipses, a little black spot in that. I went ahead and measured it anyway, just for the heck of it. So then I plotted it as it passes through focus. So I'm going to go back and forth with this, and you can see if this mirror if the system was really good, these guys would converge to within an area disk and then diverge. So I'm just going back and forth here, and you can see how they converge and then diverge. Well, there's a couple things that are going on. One is right there is the smallest bundle I can get with this particular mirror, with the mask in the position, with the black paint on the edge of the mirror, and the camera not perfectly registered. And you can see that the bundle's smallest size is about 0.003 inches in radius. It's just one problem with that. The area disk on a 12-inch f5 mirror is 0.00013 inches. This is about 0.003 inches. So this is like 25 times bigger than it should be if the mirror was good. The other thing you'll notice is you can see as I move back and forth, you can see they kind of spiral as they move. I'd ask if you could see that, but I know you can't answer back because your microphones are muted. But I'm going to just say they're spiraling. Well, that is not the mirror. That is, if you can look at my little screen here, my mask has these radii, and my camera is this way. And if my camera and my mask are tilted with respect to each other, even just a little bit, then this happens. And so that's a couple of issues I've got. One is the spiraling, and the other is the bundle's not small. Part of that is due to the fact that the camera was not registered with the mask. So I had to come up with, how am I going to get this camera registered with the mask? And I came up with a way. So I went out and shot another one with my camera registered. And so here we go. I'm going to go in and out on this one. And there it goes, in and out. And there were issues with this one too. It still spirals a little bit. But my smallest bundle, which is right there, has an outlier. That outlier could be a mask orientation issue. It could be a bad spot on the mirror. It could be the fact that I'm shooting over the edge of the mirror that's partially blacked out, and it confused the arithmetic of the linear equation between the mask hole and the target on the CTD. But look how small it is. Instead of being 0.003 in radius, it's about 0.0. Okay, that's a big one there, and that's a big one there. But on the average, they look like they're about 0.0015. So now, in general, they're only about 10 or 12 times bigger than the area disk is supposed to be. So now that I've removed some of the paint, I'm going to do a better job orienting the mask. My hope is when I go back out there and shoot it again, I get an even tighter bundle of light. So one of the things I really like about it, I'm going to go to the previous one. And so right here, can you see it's long this way and short that way? And if I transfer through, it isn't. So this is how powerful this is when you're looking for things like astigmatism. Now for spherical aberration, the nice thing would be if these dots, keep in mind that when I take a picture, the camera's 3 inches away from focus, and now using the arithmetic, it is, oops, well, I just hit the wrong button there, didn't I? Click. Okay, here we go. Let me alter something. Okay, now when I do that, you see these holes here. If this is really close to being in focus, and so if this were really well done, these holes would all line up 5 dots there, 5 dots there, 5 dots there, 5 dots there. There were no spherical aberration. But when they start getting messed around, like right there, you can't tell their radii. That's because some zones are overcorrected and some zones are undercorrected, so the lines don't pass through in the same orientation. So when I can make this bundle down to 0.00013 radius, then when I come all the way out here to 0.005, they'll be nice linear radii. They'll be all lined up and they'll look great. So my test, I'm going to do my stop share screen. You should see me again. Everybody see me again? Give me a thumbs up and see me. Okay, good. So once I get this phase mastered of this spreadsheet, mastered to my degree of expectation, then I'm going to add a millilacroid graph, so it'll tell me the slopes of each place on the mirror, because Lonnie and Bill and I and almost every other optician on the planet can use a millilacroid graph to see where the slopes are, to think in their brain, where do I need to correct the mirror? So like if we're doing a Zambuto type of correction, I would look at somebody that's undercorrected, and I would do my right size lap with the right overhang and then the right offset to wear that guy down. The idea is to wear them all down so that you have no unrealistically large undercorrections. Once you get an overcorrection, you're screwed. But you try to control all those undercorrections. So one of the things I'll add to this, once all this working to my satisfaction, the first one I'm going to get was that bundle of dots. They need to come down and show me that they're bundling and they're not astigmatic. The next one will be the millilacroid graph, which shows me the slopes on the surface of the mirror. And then the one after that will be a profile graph, which takes the millilacroid graph and shows what the profile of the mirror is, only instead of one profile, because it's a sit test, it'll be 8 radii or 4 pairs to make a diameter. So right now when you do a sit test, the right side and the left side look the same because you don't know that you've got a 2-dimensional problem. But with the Hartman test, the one on the right and one on the left may be the same or may be different. So each 8 of these 8 radii will have their own profile. And the trick is you wear down the high spot until your profiles are to the degree of satisfaction. The Struhl ratio of 80% would be a quarter wave mirror, but with our sit test, I mean, we're way past that. We're down 16th, 20th. We're measuring things at an incredibly small wafer in there, and a very high Struhl ratio. But I have good news and bad news. The good news is this test should show me everything. The bad news is this test should show me everything. I'm going to find out my mirrors stink. So it's going to cost me more time and energy to get a mirror to the numbers I want, knowing all these other radii are no longer making me happy. Okay, that was a little longer than I thought it was going to be. I hope I didn't bore the crap out of you on that. Yeah, that's my version of the Hartman test.
Yeah, let me ask you a question.
All right, thank you.
Jeff?
Any questions?
Yes.
Oh, I'm sorry, Francis, what's up?
You're using, my understanding is you're using, or you're performing this test with the optic in the telescope. Am I understanding that correctly?
Yep.
And you're using Polaris as your collimated light source, is that correct?
Yeah, and I know it's a double star, but the primary is 3,000 times brighter than the secondary, so I do just get the primary star's image, and that secondary star doesn't seem to disrupt it.
Yeah, no, that's, yeah, I understand that. I wanted to understand that you're using a star as a collimated light source. That was really the question.
I am,
And you're testing the system, not the optic per se itself.
exactly.
Okay, thank you.
So the other thing I calculated was, in a 30-second exposure, how far does Polaris move? And it doesn't move far enough to mess up the test. But if it were a 5-minute exposure, I'd have a problem. But I really like the fact that the telescope's at 38 degrees, so the mirror's resting in it like it does when you're looking at almost anything else. It's sitting in the cell that's going to be used for the optic. It's using both the primary and the secondary, and the collimation and the structure to evaluate the system. And the thing with that is, when you do finalize the project, your primary mirror will now have to be oriented the same way with the secondary mirror and the focuser as it was when you tested the mirror. Theoretically, if you put it in a different rotation, it may not be a surface of revolution, but the best situation for that particular secondary mirror and collimation. And I might find out that this just stinks and forget the whole thing, but I don't think so. I think it's going to kick some serious butt. Lonnie, who's on center of my screen, wave your hand, Lonnie. That's Lonnie, there you go. He's been doing what he's calling the easy Hartman test. And it's a shock test using the mask like I've got, and a hole, rebounds, comes back and focuses, and then he gets a right side and left side, a top and a bottom, and then these diagonals, and he gets beautiful Mill-LaCroix graphs that shows the mirror, and he just works them until they're all within, 2.5 times better than diffraction limited optic. And it's a beautiful thing to see. However, his mirrors are smaller than mine, thicker than mine, and slower than mine. And when I tried doing this, my gravity was bending down the top of that mirror, and I couldn't pull it off. And I tried, and I will try some more, but his easy Hartman, we've been talking about on this Oregon Works thing and the HM thing. His easy Hartman is really making some incredible mirrors, and the screw ratios are reliable when it's when you got 40 holes. It's way more reliable than if you got 15 holes across a line. So Lonnie's an excellent mirror maker and really a good spreadsheet writer. Spreadsheet writing is not my thing. I can't write a macro to save my tail. But I'm taking it from Lonnie and from Bill to get this thing whipped up, because I think if I could show that this 2-axis test is better than sit test, it got something good going. Dale Eason, he's in Minneapolis, is trying to take Lonnie's easy Hartman and put it into a executable program that will actually show the type of surface on a mirror like the like he does with the Fringe XP type of software for interferometry. So I'm looking forward to seeing how he pulls that off for Lonnie's test.
Hope you're able to bring some of this out to Stellafane when you retire. I know you're saying you're retiring in 3 years, and for the last 10 years, you've been saying you're retiring in 3 years. So when that day finally happens, we look forward to seeing you. And quite honestly, all the rest of you, if you make it out to Stellafane, please look me up, and I'd love to give you a tour of the facility.
What you guys all don't know is that Francis and I have known each other for decades. We've never met face to face. And I'm really looking forward to that. And I can't ever come to Stellafane because our school starts on August 1st, and you always do it like the second week of August. I can't walk out of my calculus class a week after it started. So
Yeah.
3 years, buddy, 3 years.
Looking forward to it.
Okay, that it?
Yeah, thank you all.
So,
All right. Very good. Thank you.
Thank you very
Jeff.
much.
I hope that was useful.
Jeff, that was wonderful. Thank you. It's always a good set of information for those of us that are limited IQ, but it's excellent. If you're planning on leaving right now, don't. We have another wonderful speaker, and that's Jerry Hyatt. He is a physics instructor, professor at UOP. He's going to talk about the speed of light and measuring it back in the old days. And it's I've heard the talk already, and it's a lot of fun. So, Jerry, why don't you go ahead and get started?
Okay, so let me get my screen going here. So I am going to talk about how Ole Roemer gave us the speed of light without really trying. And it wasn't that he wasn't trying to do something, he just wasn't trying to measure the speed of light. He was working on the longitude problem, how to figure out how far east or west you are from a point on the planet. Latitude was really easy. In the northern hemisphere, you just figure out how high the North Star Polaris is above the horizon, and that's your latitude. There are other reference points around the globe. So latitude, figuring it out at sea was not a problem. Longitude was tricky because longitude is time. If your local noon occurs 3 hours later than a local noon at some reference point, then you are 3 hours out of 24 of the way around the globe. In other words, you're 45 degrees west of your reference point. Now, the problem is clocks didn't work at sea. You couldn't measure that 3 hours you were a difference between the local noon. Not until the 18th century were clocks made that could work at sea well, and that's another story. So no clocks at sea, no longitude at sea. So everyone knows Galileo. He also tried to measure the speed of light. Again, that's another story. In 1610, he pointed his telescope at Jupiter and discovered that Jupiter had 4 moons. These are the Galilean moons. And a moon or a satellite has an orbital period that is very regular. And Galileo thought that they could be used as clocks. So this is what he proposed in 1616. So Io is the closest moon to Jupiter, and it has an orbital period of just 42.5 hours. Since its orbit is parallel to Jupiter's orbit, it is eclipsed by Jupiter every single time it goes around. It goes through Jupiter's shadow every orbit. Sometimes we can observe Io going into the shadow. We call that an immersion event. And we can also observe Io coming out of the shadow. That would be an emergence. So a ship's clock, theoretically now, it would just have to measure the time of some Io event, either an immersion or an emergence, measure it from its own local noon. It still has to measure some time. And then that time of immersion or emergence could be compared to a table that had these times for some reference point. Well, guess what? Not only was it difficult for clocks to work at sea, but for many of the same reasons, it's difficult to make astronomical observations at sea as well. This idea was just too difficult to work. But that doesn't mean that people on land thought, hey, we should try that. It's just kind of cool. Giovanni Cassini was the designer as well as the director of the Royal Observatory in Paris. And so he was looking at these periods of Io, and he noticed that there were variations in the measurement of something that should be constant. So we wanted to investigate these and think of the time period, late 1600s. Where would you go outside of Paris, his own observatory, to get accurate astronomical measurements? Well, I would go to Tycho Brahe's Uraniborg, of course. So Cassini sent Jean Picard, who was another prominent astronomer of the day, and his name was John Felix, not Jean-Luc. Unfortunately, Jean-Luc Picard would have been so cool if he were actually named after an astronomer. But anyway, Cassini sent Jean Picard to Uraniborg in Denmark. Well, who is in Denmark? Well, this is an older picture of Ole, but at the time he was a young graduate from the University of Copenhagen, and he had the job of processing all of Tycho Brahe's data for publication, which meant that essentially he had inherited Uraniborg. So 1671, Picard arrives, and together they measure 140 eclipses of Io. Then with Cassini, they determined the difference in longitude between Paris and Uraniborg using the Io data. So they proved that Galileo's method could be done. You just had to have really good astronomical tools in order to do it, not the kind of tools you could throw on a ship. So Roemer went to Paris in 1672, working with Cassini, and they combined all of their data. And basically, Roemer had confirmed the anomalies that Cassini had measured, indicating they weren't necessarily instrumental anomalies, since they were measured. Two very good separate measuring devices show the same differences. What Roemer did that his other two colleagues here couldn't recognize was that he could show that these anomalies were due to light having a finite speed. Not very much of Roemer's work survived. There was a great battle in Copenhagen. I don't know my history of the era. There's the Battle of 1808. I don't know who was at war, but most of Roemer's work was in the library in the university in Copenhagen and was destroyed. Miraculously, this sheet of his data did survive. You'll note that, like here, this is 1669 right here, if you can see my mouse. And he's got a time, and this is an immersion event. This is the date. And so this is an immersion. Here we have an emergence, immersion, immersion, emergence. So we have a page, and this spans actually several years. There's 1678 down here, 1673. And so quite interesting. I'm going to have to go through this because I tried to look up some of this data in our Observer's Handbook. And on page, I think it's 320, it lists the emergence and immersion data for Io, but it doesn't give the times to the second. It only gives it to the minute. Anyway, so Roemer's explanation for the anomalies. Kind of ignore this sinusoidal thing down here. At first, I imagined that the readings would be sinusoidal. You'd have some times that were a little longer, sometimes that were a little shorter. And it kind of made sense, but when I thought about it mathematically, I thought compared to what's going on physically, I thought that, you can't have the steep slope at these points, but that's another story. Here is the drawing that Roemer used in his explanation. So you have the sun, the Earth's orbit around the sun, and Jupiter, and Eo's orbit around Jupiter. Behind Jupiter, of course, we have its shadow. So if you imagine that Earth is here at point L, and at that point, Io comes out of its shadow, and that point is recorded. Now, it's only 42.5 hours till the next orbit. So this drawing isn't to scale, it's for explanatory purposes only. So let's suppose that as Io goes around its orbit and comes back out again, the Earth is all the way here to point K. So Roemer was claiming that the reason this period looks longer sometimes is because it takes light to travel, time to travel that distance. I'm skipping over some of my, whoop. Oh, that's nice. I just lost. Am I gonna have to go through this all again? What happens when I talk too much and I forget to click my slide? Okay. So the average period, 42.5 hours, you would get that right here at this point H, which is opposition, which is coming up on July 14th, I believe, where Jupiter will be opposite in the sky from the sun. And down over here, we have what we call conjunction, where from Earth, when you try to look at Jupiter, you can't because it's being blocked. It's in line with the sun. And I think we had a conjunction last December 12th. Okay, so this time period from opposition to opposition is not a year. This is not just Earth going around the sun, but coming back to Jupiter is actually 13 months, as I say down here. So yeah, at this point, at opposition and conjunction, we can't actually view the eclipses. But when Earth was traveling in one of these positions, like from L to K, the period is longer by about 16 seconds. Now, if we see an immersion event, Io going into the shadow when we're at point F, and let's say the next one we observe, Earth has moved to G when it goes in again, and that's shorter by about 16 seconds, okay? And again, not to scale. So Roemer realized that these effects, only 16 seconds for each out of 42.5 hours, very small time to measure, but he realized that these times would add up over several orbits. So what he did is he timed 40 periods of Io while the Earth was moving away from Jupiter, 40 periods while Earth was moving towards Jupiter, and he added up the total variations, the variation from the average values. And he concluded that while Io underwent these 80 orbits of 42.5 hours each, Earth had moved the distance over which light traveled for 22 minutes. Okay, so he could compare the speed of light to the speed of Earth. So the ratio of the two times is 80 orbits of Io times 42.5 hours each. Convert that from hours to minutes. And on the other hand, so this would be the distance the Earth well, the time Earth would travel. And in that same distance, then light traveled for 22 minutes. So the ratio of the two times is 9,300. So light must travel 9,300 times as fast as the Earth does in its orbit. Now, the actual recording from the meeting where he presented this also did not survive. Mostly what survived were news reports. And so besides this version of it, another news report simply claimed that the speed of the light must travel 2 times the Earth's an astronomical unit, the distance from the Earth to the Sun, in 22 minutes. They give about the same value for the speed of light. He never actually reported a speed of light other than that light must travel about 9,300 times faster than the Earth. Okay, but others using his data did perform some calculations, and they had various reports figuring that lights traveled somewhere between 140,000 and 170,000 miles per second, just a bit slower than the accepted value near 186,000 miles per second today. So problems that Roemer had, not everybody would accept his explanation, even though, you know, there was no other viable explanation at the time for these aberrations. People had trouble believing, first of all, that light had a finite speed. His 2 collaborators in making the measurements, Cassini and Picard, neither could imagine a finite speed of light. But the story about them, they made another observation. They observed what's called stellar aberration, and that turned out to be another way to measure the speed of light. And they passed over on that as well. So the speed of light, you can't hardly blame them, because the speed is so fast that it is almost unimaginable. But they twice missed out on having the data in front of them that would have allowed them to measure the speed of light. Some people were wary because of some of Roemer's calculations with the orbit of Jupiter were based on elliptical orbits, which were suggested by Kepler not too much before this, also using data from Uranoborg. But Kepler's ideas weren't widely accepted yet either, okay? So he had trouble getting his point across. Now, on the positive side, people who accepted his explanation almost right away: Edmund Halley of comet fame, Christian Huygens, and Isaac Newton, all of them accepted Roemer's conclusions right away. Now, an interesting thing about Christian Huygens and Isaac Newton is that even though they agreed with Roemer in this case, they held quite opposite beliefs from each other regarding the theories of light. Newton believed very strongly that light was composed of particles. He called them corpuscles. Huygens, of course, was the first person to propose a wave theory of light. So they had very different ideas about light, but they both agreed that this explanation that Roemer offered is the best, and definitely showed that light had a finite speed. Huygens kind of needed light to have a finite speed because he had a theory of refraction that required light to have a finite speed. And previous to this, I think around somewhere between 1650, 1670, a mathematician named Fermat also figured out a theory of refraction, how light bends when it moves from one medium to another, that depended on light having a finite speed. So there was acceptance, some acceptance anyway, of this finite speed of light. Thank you very much. Are there any questions? And I'm not hearing anything. Is anyone still here?
I think everyone went to bed, Jerry, but nonetheless, that was outstanding. Thank you very much. And as always,
Jerry, I have a question.
Yes.
Jerry, so this works with Jupiter and Io. Is it only for Io because it's on the same plane as with us, or are there any other moons on other planets that the same measurements could be made?
This was an argument that people had against Roemer. and Roemer's ideas, and that is that the this discrepancy, this anomaly, was not noticed in the other Galilean moons. But those orbits, those orbital periods are much longer, and such a small deviation would have been very difficult to measure and to show for those cases. And there are other reasons which I have not delved into. But yeah, that's one of the things that people that opposed his idea brought up.
Thank you.
You're welcome.
Good job.
Thank you.
Okay, so I hope you noticed that every lecture was totally different from the other one. Hopefully it made it more interesting for all of us. I found them all challenging, interesting. Jeff, I don't know what the heck you're doing, but anyway, it's good. Very enjoyable on that. For those of you that have attended from back east, and it's past midnight right now, we want to thank you from the bottom of our hearts from attending the meeting. And also, we'd like your input. We're trying to make this into something that's workable and viable, so that as long as this COVID thing is going on, and perhaps even beyond that, we'll be able to have these meetings and perhaps even have some wonderful speakers from around the country that don't have to come and visit us directly. So again, thank you all. I'm going to close this part of it. Jeff is going to present a raffle prize that we normally do at our meetings. So I'll leave it up to you, Jeff.
Well, he's passing up to me because I'm so good looking.
Now he has the gift.
So I did a raffle, and I did a logical, fair way of determining who's going to get this. What I have is a Orion O3 filter in a 1 1/4 inch focuser size. And I did have a winner. It looked like she clicked out. Oh my goodness. Did Olivia really go? Olivia left.
Oh, Olivia's here.
Where? I thought she was here, but I don't see her.
She's here. There's a CC in her window.
Oh, there she is. Can you
She just flashed back.
Can you put her microphone on?
She has to turn it on herself.
Click on your microphone, Olivia.
There you are. There you. I got.
You won a filter. Do you have a telescope with a 1 1/4 inch eyepiece?
No, I don't. I don't have.
Well, do you want to check out a telescope so you can use this, or I don't know what you'll do with it without an eyepiece.
Oh, I don't know.
Well, you won it, and what an O3 filter does is when you look at nebulas like Orion Nebula or something like that, and it's light pollution, you put this thing on, and the sky goes dark, but the nebula keeps shining through, so it makes it easier to see. So you can decide if you want it or if you want me to get you something else.
Maybe something else.
Okay, so I'll tell you what I'm going to do. I'm going to get you something else, and I'm going to give this to the runner-up. I did a little scheme here. The runner-up was, Bill, are you still here? Bill Lytell, didn't you already win something from us?
Yeah.
You're the luckiest guy. Not only you're lucky on this filter, but you're lucky that she's going to pass it up for something else.
Thank you, Olivia.
You're welcome.
So this originally came from Gerald Smith, and he passed a lot of equipment on to me, which I have passed on to a lot of people. And this is a straggler. So Bill Lytell, congratulations. You just got an Orion O3 filter. And Olivia, I'm going to come up with something really good.
You're going to Disneyland, courtesy of Jeff.
Hey.
Yeah, great.
As long as it's not on a cruise ship, huh?
So what do you have, Olivia? Do you have binoculars or anything like that?
Yeah, I do. I have binoculars.
Okay. Do you ever look at constellations or find things in them?
Oh, I'm constantly doing it. Yeah.
Would it help if you had some kind of some kind of star chart or guide like that?
Oh, yeah, I would love to. Yeah.
All right. can you sit here for just a second? I'm going to show you what you just won.
Sure.
So excuse me, while we wait for Jeff, Mark Gibbons, I've noticed that your background has changed a couple of times. You've been doing some star travel there. So why don't you give us a little description of what the background is that you've been showing us?
Oh, well, right now, can everybody hear me?
Yeah.
Okay, good. This is an image I captured back in, let's see, that would be March of '96. It's Comet Hyakutake. And I piggybacked that on one of my scopes. And I think I captured it on Kodak 1000 film.
Wow.
So, yeah, at the time the lecture was going, I didn't think anybody could see what I was doing, but I was just playing with the backgrounds. Those are images that I've captured, various images I've captured,
Yeah.
mostly from my backyard.
Very nice, very nice. And what was the one prior to this? It looked like it was like the Ring Nebula, but is much larger than I'd ever seen.
Oh, well, let's see. Was it this one? No.
No.
Oh no, it's this one. There was that.
Yeah.
Yeah, that was. Let me get rid of this.
That's a planetary, isn't it?
No, it's a star forming region in Monoceros. This was interesting. I captured this about a year and a half ago, probably quite a while ago now, from my backyard in Tracy. Before they put I have a road that runs near my house, and this was before they put the LED lights in. And now I can't do anything in my backyard, so I'm dependent on star parties to capture images. But yeah, I used to be able to capture pretty decent images from the backyard, and this was one of them.
Oh, wow.
Oh, it's a beautiful photo.
No, thank you.
That's awesome. It's beautiful.
Appreciate that.
Olivia,
Yeah.
here it is.
Oh, yeah. Whoa.
I can't find it, but I have a chart system that will let you be able to find things in the sky. I thought it was over there, but it's not. So I'll get it and I'll get it to you.
Okay, great.
So congratulations.
Oh, fantastic. Thank you. Okay.
Okay, folks, I think that just about sums it up. If you still want to chat, that's fine. But as far as the meeting itself, that's pretty much our presentation tonight. I hope you all enjoyed it. If you haven't guessed, we have some outstanding members in our club and acquaintances as well. We got Lonnie, we got, and I can go on and on. But they're just some incredible people that are involved in this whole thing. So I'm hoping this will be something that in the future will be appreciated and used, utilized. And if we can make this happen, it's just going to give us one more wonderful dimension to make the club and all of our friends and associates communicate with us and to make it a better world. So thank you very much. Stay safe. Practice social distancing, not like Jeff and I do. And we should be fine.
That's you.
Thank you, sir.
Good night, everybody.
One more thing, guys. Could you, if you get a time, could you shoot the executive committee a quick message saying what we did right, what we did wrong, what you never want to see again, what you want to see again, just kind of give some feedback so that we can do this better and better and better each time.
As long as it doesn't involve the president, we're good. Meaning me, not the big guy.
Thank you all. Clear skies.
All right. Very good to see you,
Good
everyone.
night, everyone.
Take care.
And Nihart, thank you for staying through the whole show.
Thank you for having such a great meeting.
Oh, you're very welcome. It's our pleasure. And hopefully we'll get to meet in person soon.
Hopefully.
All right.
You know what I want to know? How are you guys getting that thing behind you? Like Bill's got a scope behind him, and Nihar's got some junk behind him, and Mark's got the drama. How are you all doing that?
It's down at the bottom where it says stop video. There's a little selection tool there. Choose virtual background. So I've been pulling my astrophotos off of my hard drive here.
Oh, I can put something really awful on it, didn't I? Okay.
How about you, Eric? Is that the ISS?
Not the real ISS, just a picture.
Actually, it was Eric's picture of the ISS that made me start looking for how to do it.
So what do you think, Jeff?
I gotta move like this, so it's more real.
I moved outside.
Oh, nice.
Does not meet criteria. I can't do it.
I gotta find some way to get some front lighting instead of some back lighting.
Ah,
All you can see is my shadow.
I think that's okay, Jim.
Yeah, I can eclipse you all.
ah.
Yeah,
Figure it out, Jeff.
normally I use my iPad to do this Zoom stuff, but today was the first time I tried it on my PC, and I'm very impressed with it. I still like Team though.
I use Teams for school. Works good.
Team is good.
Jim,
Good night.
how y'all doing?
Yeah, can I make a tip here for everybody? This is Jim in Rio Vista. This headset I'm using for the audio cost me like $12 in my Amazon on it. And I think everybody's audio would improve immensely if you went to a boom microphone and get rid of that sound that sounds like you're in the bottom of a 55-gallon drum.
I might happen to like that sound. What do you call it? A boom microphone?
Yeah.
Yeah, his headset there.
It's got a little teeny boom microphone off the side here and the speaker. The other thing I've done too is I had an extra set of high fidelity speakers that I plugged into the laptop with a subwoofer and the left and right speakers, and that improves the sound tremendously over using the speaker that's in your laptop. It sounds almost like television then. So it's only depending upon the incoming audio then coming from people. Like Jerry's audio is actually pretty good, and Jeff and Mike's audio was actually pretty poor as far as I was concerned. I can hear here. So and Jim Shutnick, yes, you need front lighting. Amelia and I probably spent at least an hour messing around trying to get the lighting right. So we're in our dining room. We've got an overhead chandelier light in front of us, about 2 feet in front of us overhead on it. And I've got a little light off to my left side, a little shop light to get some extra side lighting so we're not backlit. So Jeff and Mike their lighting actually looks pretty darn good.
Is that a Christmas tree?
Yes, it is.
Pretty late or early?
No, it's been up, it's just late. I have a collection and no place to store it, so it lives there.
That works.
Well, just a tip. So we've done a lot of Zoom meetings with our radio clubs on it, both local and across the United States. So I've seen enough of this to know what works and what doesn't. And definitely consider a little boom mic like I've got here. That, like I said, it was like 14 or 15 bucks to live with tax delivered from Amazon in 2 days. So
well, our sound is my fault because they told me the other day when we practiced that I sound better from back here than I do up front. So the second my thing started, what do? I went right up front.
Actually, it doesn't make any difference.
Okay.
It's got a boom.
With your sound, Jeff, yeah, the automatic gain control on your computer is automatically adjusting on it. So as the automatic gain starts cranking up the microphone gain on it, you start hearing more and more background within your room. on it. So if you have hard walls or a hard floor, hard ceiling like that, you get the echo effect on it. So ideally you'd want to be in a carpeted room with drapes and such like that behind you, and that'll help get rid of the echo.
Hey, Mark.
Yeah.
That set you've got on, is that an iPhone set?
Clicked you off. Yes, it is. It was an extra one that I had. Oh, that's not it either. I've lost everybody. But anyway, yes, it is.
I hear good sounds from it, so.
Oh, good. I was going to ask if it was pretty good audio.
Yeah, that sounds quite good.
Great.
So
I'll have to
I'm
dig
using
some of mine out.
microphone. Is that coming across okay?
Yeah, Jerry's audio is actually pretty good.
Ah.
I assume you're just using the microphone inside your computer.
No, I have this guy. You can see it here.
Oh, you got a real.
Oh, he raided the school supplies.
No, it was 26 bucks from Amazon.
Wow, big spender.
But we needed a microphone that we could both speak on for family stuff. Because I had a headset microphone, and then we had to share the microphone part of it.
What is it, Jerry?
The microphone itself?
Yeah.
Heck if I know. It's CM Tech. CMTECK. Studio USB microphone. Yep. I gotta get rid of the background.
Well, we'll get better at this as we do this over and over and over.
Hey, question for Jeff. About, oh, cool. Question for Jeff.
Yeah.
I'm assuming that if you used, were testing conical mirrors, you wouldn't have to worry about the distortion caused by gravity.
You would, but it would be, it'd be better. The ticket is a meniscus mirror. The conical mirror is very similar to a meniscus mirror, but what I've been hearing from meniscus mirrors from Mel is that he just puts two posts on it, stands it up, and it's just fine. And it's only that thick. The conical mirror, we had one in Greg Wilhite's scope, and I did test it, but it was mounted in the center using it's almost like a baffle in the middle. That's how they actually mounted it to the cell. Didn't have any other parts, just that one thing, and it was just fine. I didn't do any critical tests with it, but it can work.
Okay, good to know.
Yeah.
You just have to grind all your mirrors conically now.
No, I got that quartz and I was thinking about that. Mike helped me slam the brakes on. What are you doing, stupid? But meniscus, I'm a fan of. Conical, I haven't done one, so I can't quantitatively tell you if it works or not, or if it's good or bad. Lonnie, you done any conicals?
Lonnie, you're muted still.
There we go. That's why I can't get anybody's attention, huh? No, I haven't done a conical. It looks really interesting the way it mounts. You'd think it'd take the stress right away, especially the edge. Wouldn't have to worry about edge pressure. But
I think the hardest part of it would be supporting it while working it.
Yeah. You'd have to figure out a way to support it on your machine.
There's always a way.
Yeah.
So how are you doing on your 16-inch that you restarted again?
Oh my gosh, that thing is a nightmare. I like Jeff says, we're testing mirrors better, and that makes it so we're testing mirrors better. My problem is I had my mirrors down to about 30 days. I could make one and have it out the door, and then I started with this Embudo process, which is a very long parabolization sequence. And I haven't learned it yet. It's been 6 months and I can't make a mirror. So it isn't so much my test. I've gotten pretty good at balancing the curves. So as the mirror comes down, I can see one side is lagging, one of the 8 quadrants is lagging. I can do a little handwork and tweak it back in. It's not too bad. But I've run into center problems and edge problems. You ever heard of a turned down edge on a mirror?
Yeah, gee, I don't know.
You don't know that one, huh?
Well, you know, the weird thing is, we thought we were doing so good until this multi-axis crap came around.
I know. So I'm regretting it.
You know, ignorance is bliss.
That's right. And of course, I'm trying to make the one perfect mirror so I can show off this test, right?
Yeah, you just show that one. You don't show the other 50, you just show the one.
That's right.
Kind of like astrophotography. Hey, look what I shot. Don't look at those over there.
Exactly right. I'm really looking forward to Jeff's test. It's really interesting to pick it right off the scope and watch the actual focus right through the focal point.
That's the coolest part of
great.
it, is watching that bundle converge and spread out again. It's awesome. What I
I'm
really want to
anxious
do,
to see how he arranges all those dots. So, I mean, how he identifies where they came from. That's going to be
well, I lied.
fun.
The best part will be when I get it done and we compare your Easy Hartman, my Baldwin Hartman interferometer in the sit test, and they match.
Exactly.
Yeah, that's the acid test, the sanity check, is that they
Exactly.
match.
So who needs to go outside when you, right here, we can observe the Shoot-necked eclipse.
There you go.
I don't see any Bailey's beads though.
He's a new
Well,
Shootneck.
what was that?
He's a new Shootneck. In a couple of days, he'll be a waxing Shootneck.
Oh, yeah.
Well, this looks like the new normal for our clubs. Sacramento Valley has no plans to start meetings.
Wow.
And everybody's been asking us, when are you going to have the next star party? We've shut that down as well. So they're talking about maybe even the rest of the year. Starbecue we normally have in late July or August. Nothing yet. I think it's going to be canceled. So
Speaking of star parties, how about our Highway 4 next weekend?
How about this weekend?
Well, that's what I meant.
Yeah. I'm going.
yeah.
We don't usually have a lot of people up there, so, you know, can easily maintain distance.
We had 4 last time. Me, Mike, Bill, no, Tim, and was it Bill? Bill. Yeah. And we had a blast. The sky sucked, but we had a great time.
Well, unless the things change, it's supposed to be pretty nice this weekend.
I'm planning on going Highway 4 Saturday and high altitude the week after that.
Way to go, Mark.
No, that's Jeff's.
Oh, that's mine?
Yeah, that's one of yours.
I never did get that thing worked out, did I?
I thought it was pretty nice. Yeah, you sent it over to me to play with, and that was all I could do. But I'm not much for
Can you
planetary and solar.
Can you send me that image sometime?
Oh, sure.
It's so small on this screen, I can't really, tell good, bad, or whatever.
Yeah, it's got some nice detail in there, Jeff. There were some nice images there.
I really wonder why mine came out with such weird contrast.
It's processing of some type. I don't know. That's a black art. You can get them to do anything.
Yeah.
Well, it looks like my big old kitty cat here is trying to bite my legs. He wants me to come feed him. So I think I'd better head on out.
All right.
James. Good night, James.
See you all later.
Good night, everyone.
Bye-bye.
Good night, everybody.
Good night, guys.
Have a good evening.
How do we go out?
There is an end button, usually lower right.
Oh, leave. There it is. All right.
There you go.
Good night.
Good night, everybody.
Good night. Good night. So I see one person just signed in. Still connecting to audio.
Shows Bob.
We'll find out in a minute. Wrong time zone, maybe.